This video covers Newton's second law, which is the relationship right here, which states that the net force is equal to an object's mass times its acceleration. If we want to look into the unit for force, we should look at the units for the variables in the force equation. So we know that the unit for mass is kilogram. We know that the unit for acceleration is meters per second squared, so we know that the unit for force is kilogram meters per second squared, which is also known as a Newton. There are certain steps to following a Newton's second law problem. First, you want to draw a free body diagram. Second, you want to find the forces acting in the x and y directions. Third, you want to set your equations in step 2 equal to the mass times the acceleration in either the x or the y direction. Then finally, you use your equations you put together to solve for the unknown value. So let's do an example. A man is lifted back into a ship after falling overboard. His mass is 80 kilograms and he is pulled up at 2 meters per second squared. What is the force the crew is applying to lift him up? So the first step is to draw a free body diagram. And we know that the man is lifted, so there's an upward tension force, okay? And the equation, we also know that he is on Earth, so he has a weight. And the equation for weight is mass times gravity. That is why we call the weight force also the force due to gravity. So perfect. Now we have our free body diagram. The second step is to find the net force acting in the x and y direction. Since we know that there are no forces in the x direction, we set net Fx equal to 0. And then we will look at the net force acting in the y direction. We know that there's a tension force acting up in the positive direction and a weight force acting down in the negative direction. So our net force in the y direction equals tension minus weight. The third step is to set this force equation, this net force equation, equal to the mass times the acceleration in the y direction. And the fourth step is to fill in the variables, and then we can solve for our unknown variable, which is tension. And we see that the tension is 960 newtons. So let's do a second example. You are riding in an elevator. As you near the top floor, the elevator slows at a rate of 3 meters per second squared. If your mass is 60 kilograms, and if you were standing on a scale, what would it read? The first thing that is important to note is that scales read normal forces. We will do other problems similar to this, a scale in an elevator, so it is important to remember that scales read the normal force. So the first step, let's draw our free body diagram. So we know that we have a normal force pointing up and a weight force pointing down. And that's all the forces that we still have acting on this person. So next, we will look at the forces acting in the x and the y direction. We didn't draw any forces in the x direction, so we still know that the net force in the x direction is equal to 0. And for the y direction, let's call up positive again. So our net force in the y direction is going to equal the normal force minus the weight force. The third step is to set the net force equal to the mass times the acceleration in the y direction. So here we have the normal force minus the weight equal to the mass times the acceleration in the y direction. And now we can plug in our known variables, taking into account that our acceleration is -3 because we are slowing down. And we find that the normal force is 480 newtons. So it's important to note that this is a lighter value than what the scale would read when the person is not accelerating. So when the person was not accelerating, the normal force would have been 600 newtons. This makes sense because when you're traveling up in an elevator and the elevator begins to slow, you feel as if you're being pushed upward slightly, and therefore the scale would say that you weigh less.